With our Winter 21 Paper 6.2 question 7. This is about electrical circuits, and we'll be given a circuit where it's set up in parallel. That's going to be important for later. We've got a bit of a procedure where we close the switch, we measure the potential difference using the voltmeter, measure the current, and then we open the switch. Okay, quite a safe and sound procedure there. We're given some analog meters. Now these are lovely relics from when I was at school. You may see these in your classrooms as well. Okay, and they're just a test of your ability to read a scale. And whenever you're looking at these scales, you're being asked to read the potential differences and currents a couple of times, I think. We're going to record the potential difference V1. Well, V1's fairly easy. You notice our V divisions are 10 divisions to every 1. Okay, and so that means each one of these guys is going to be 0.1. Okay, so we're measuring to every 0.1 of a volt. We've got 2, or 1 after that, 2.1. And that's what the answer is in the mark scheme. Okay, here we've got, just to check, 5 divisions going from 0.5 to 1. Well, therefore, again, we've got a division here which is 0.1 each. Now, the tricky bit comes that our pointer is halfway through. And I don't really like these kind of questions. I get a bit nervous about them because in real life, you will never really find a pointer pointing directly halfway through, halfway between 2 points. And in fact, what you might be tempted to do is say, well, I will choose the value which is nearest to this. That's certainly what I was taught when I was at school. Okay, now CIE wants you to go in between the two. Okay, and so therefore actually what you're measuring here is 0.85 amps. Okay, in other words, we are certain, or fairly certain anyway, that this thing is pointing directly between 0.8 and 0.9 and therefore 0.85. All right. As I say, some people, your parents perhaps, if you spoke to them about it, may object to this a little bit. Okay, I certainly think it's a bit questionable, but that's the game we're playing. Okay, so we'll carry on. We're being asked to calculate the resistance. Now this is a core paper, and so therefore R equal V1 over I1 is given to you. Okay, that's the definition of resistance, the ratio of potential to current. Okay, we are then going to calculate that. 2.1 divided by 0.85, 2.47. Okay, and we're giving it in ohms. Now if you look in the mark scheme, you get a mark for the value. Okay, all of the working I've done here is probably not necessary, but I like to include it anyway to keep myself right. Okay, you've got to remember that you've got to have a symbol of ohms there as well. Okay, so we know that resistance is measured in ohms. Okay, we're then told the student rearranges the circuit, so that the two resistors are connected in series, and we're asked to draw the circuit. You don't need to include the ammeter and the voltmeter. So if we go back, we're basically taking this circuit and rearranging. Okay, power supply and switch, we're going to include them because it doesn't tell us to take it off. Okay, but it does say don't worry about the ammeter and voltmeter, just connect them in series. Well, as you know, series is just a long chain, okay, with the two resistors next to each other. And this is where I kind of like showing my answers, because I do notice that if you look at the mark scheme, this is what they want from you guys, okay, but you may not know what two resistors in series looks like. That's what this is down here in the bottom there of my branch, my circuit. Okay, let's have a quick look there. Okay, we're asked to suggest why the student opens a switch. In other words, why would you turn off a circuit while you're using it? Again, I would hope this is fairly sensible. Okay, all right, okay. However, I'm noticing now, whoa, a panic alert that my answer, okay, doesn't quite match with what the markers have said. Okay, they've said so the resistors don't heat up, okay, or that we don't waste the power supply. I think this is completely fair enough. However, remember, the mark schemes are not exhaustive, and an absolutely sensible answer here would be to prevent the risk of any kind of electrocution. Okay, it's a safety consideration, and it's a completely valid answer. Now the question is, would CIE accept that? If you're not sure, if you want to take a gamble, okay, go with, you could talk about safety in terms of electrocution. However, they're saying heating up. Why not play the game and go with these guys, okay, in terms of resistors not heating up and also power sources not running down, okay? Up to you. I suppose because we are dealing with fairly low voltages, you wouldn't expect you wouldn't expect any kind of shock in this case. So maybe I'm being a little bit over the top. I'm a bit over the top at times, that's fine with me. Okay, We're then asked to calculate the resistance again, for a second time. Okay, R2 equal V2 over I2, and then we've got 9.52 ohms. The answer here is 9.5. You'd be fine with either, okay? Do not worry about that. And then finally, we're asked to compare our answers, okay? And this is the crunch. I've sort of talked with my students about this, and I want to kind of make this very clear. The teacher tells us that R2 is equal to 4R1. We're asked to use your results from A2 and B3 to state if, allowing for experimental error, the teacher's statement is correct. Now, I think this is quite a high-level question for a core-aimed paper, and so I really do encourage students to think about this quite heavily. What this is saying is that those two numbers, R2 and 4R1, should be the same. If you work them out, R2 is 9.52 and 4R1 is 9.88. So they're clearly not the same. However, we have to work out how similar they are, because in physics nothing is the same. Okay, you can always delve into a number deeply to find that numbers are not necessarily going to be the same. So the question is, how close do they have to be in order to be considered constant? Well, if we calculate the percentage difference, in other words, we take the numbers away and divide by the bigger one, we'll get an idea of that. And in this case, we have 9.88, take away 9.52, all divided by the 9.88, and we get a difference of 3.64%. Now, in the great scheme of things, that is not a very big number. Okay, in other words, it is within experimental error. And the question here is, what is experimental error? Experimental error is about 10%. So if you're doing these questions, you will notice this kind of value chucked around very often. It's a kind of unofficial figure for physicists which says if you're within 10%, if the two numbers are close within 10%, then we will accept them as being good answers, as being the same number. Okay, so for example, if you take the two numbers 10 and 11, well 10 and 11, well there's about 10% between those two numbers depending on how you look at it, and so therefore are they the same? Well, you could argue that 10 and 11 are the same. 10 and 12, however, probably not. All right, so we have to argue in terms of percentages, in terms of numbers, and so the fixed thing that we tend to use, even though it's not really written anywhere, even though it's kind of one of those hidden things, is about 10% should be okay. If you're getting a number above 10%, then you probably want to answer no to this question. Okay, small heads up, I've noticed with all of these questions, they tend to be yeses. Okay, tend to be very similar numbers. Okay, very rarely will you get one where actually it's a no. Every now and again you get them, okay, and we'll hopefully find them in the course of our videos. That's enough from me. I've blabbered on enough, all right. I hope that's all clear, and please do let me know if you've got any questions. Thanks for watching.